Hey guys, this is Karthik. In this video, we will talk about disjoint set data structures and the operations provided by these structures, namely union and find. So if you want to solve some tough problems or you are just interested in knowing more about data structures, this video is for you. So we're going to talk about a sample problem on graphs and we'll try to solve that problem. Incrementally, by learning disjoint set data structures, we'll see how we can improve the complexity of the initial solutions we come up with. Now here is a sample problem for you. You have a graph. This entire thing is your graph. And you'll be given queries of the form u comma v. You have to tell whether there is a path from node u to node v. So if I ask you a query, hey, is there a path from b to c? You will tell me yes. But if I ask you, is there a path from d to f? You will tell me no, there is no path. How about d to a? There is a path from d to a, so true. And your graph has v nodes and e edges, and we should note that e can be up to v square for a fully connected graph. Now try solving this problem. I'll give you a few solutions. So the first solution is that for every query I'll just perform a BFS or DFS. So let's say the query is u comma v. Starting from u, I'll perform BFS, and complexity of BFS is v plus c. Since I have q queries, overall complexity will be q times the complexity of BFS. And since e can be up to v squared, it ends up being big O of q times v squared. Now q can be very large. So we'd like to remove this q from the factor of multiplication into v squared. Let's try a better solution. So how about I perform some pre-processing? For every node, I do a BFS and I store all the nodes that can be visited from node X. Now per query, I can answer in O1 time. So that is good, but still the pre-processing time is v times the time for BFS. It ends up being v cube. So this is slightly better if your q is greater than v, but otherwise it's still a cubic solution. Can we do better? We actually can, but for that we have to learn disjoint set data structures. So what is the disjointed data structure? Now, a disjoint set data structure is a collection of k sets, and every set has some elements. Overall, you will have n elements distributed into k sets, and each set will have a representative element. No element among those n elements will belong to more than one set, and every element will belong to at least one set. Is that too complicated? Maybe a little bit, but a diagram would help. So you have 8 elements here, and those elements are A, B, C, D up to F. They have been divided into 3 sets, and these are disjoint sets. No set overlaps with the elements of other sets. So S1 has A to E, and no other set will have the same elements again. Overall, this is your D, the disjoint set data structure, a collection of 3 sets here. Now, every set has a representative element. So S1 has one representative element, and maybe let's call A to be the representative element. For S2, let's say G is the representative element. Similarly, for S3 only F is there, so F will be the representative element. Now, there are 3 types of operations that can be done using a disjoint set data structure. They are namely make set, union, and find. As highlighted here, make set, find, union. So when I tell it to make set, what happens is the disjoint set data structure, let's say I say make set F, it will create a new set which will look exactly like this. It will have one element, and that element itself will be the representative of that set. So this is make set F. Now there is another operation called find of X. So here find of B should return me the representative of the set to which B belongs, which is A. How about find of E? That will also return me A. How about find of F? That will return me F. Similarly, find of B and find of E return me A. That means B and E belong to the same set. So this is a high-level abstract introduction to what a disjoint set data structure looks like. Have this in your mental map and the three operations we talked about, and we'll try to implement it through data structures. So how to use a, let's try to use this disjoint set union using the three operations you have to solve the actual graph problem. So initially you have a graph with V nodes, E edges. For every node, let's make a set. So I'll run make set U for every node of the graph. And I'll end up having something like this, A, B, so until I believe F. And these are all separate sets, S1, S2, so until S8. Now for every edge in the graph, I will run union U comma V. So if there is the edge from A to B, I'll union A and union B. So union A comma B. And this will become a single set. Essentially, till you have, once you have done these two operations, you're going to end up what you saw in the previous image, which is this thing. Once you have make set for all the nodes and then union for every edge, you will get this thing. Now, how do you solve the queries? For solving the queries, all you need to do is find of u equal to find of v. If they belong to the same set, that means they're a part of the same connected component, and you have a path between those two nodes. But otherwise, you don't have a path between them. So for each query, you just need to check out for the given two nodes, are they part of the same connected component? That means, are they part of the same disjoint set? Now, overall complexity of this is going to be, you will run make set v times, then you're going to run union e times the number of edges times, and you're going to run find the number of query times, so q times find. So we have the time complexity overall using a disjoint set data structure. We need to find out what is the best we can achieve for make set, union, and find now. Let's go to one implementation of a disjoint set data structure. So this is a linked list implementation of disjoint set union. What we have here is a set S1 that has a tail head pointer to the representative element of the set and a tail pointer to the last element of the set. And every node has a back pointer to the set they belong. This will help you in answering find of C very quickly. Find of C will be S1 head pointer A. The representative of the set C belongs to is A. Similarly for E also, follow the back pointer to the set and then use the head pointer to reach A. So you have structures like this, and this is the same thing that we have in the previous illustration diagram as the disjoint set linked list implementation. Find is very faster. Make set is very fast. All you need to do is set up a node or create a new set with a new element, point the head to F, point the tail back to S3. That's it. Point the back pointer to S3. So it's going to be constant operation. So both make set and find are one, but how about union? So union is going to be slightly costlier. Why is that? Because whenever you try to union something, let's say I try to union S3 or F comma C. So if I try to union F comma C, what will happen is S3, S1 will be attached to S3. And this is how it will look like. You will remove all these, this S1 from here. F's pointer will go to A. All the back pointers of A, B, C, D, E will go to S3. So all these pointers, 1, then 2, then 3, 4, 5. All these pointers have, the back pointer of these elements have to be mapped back to S3. And then, yeah, some pointer changes, but majorly the effort there is that every element's back pointer needs to be mapped back to S3. And that is a costly operation if your set that you are making union, if the second set is longer, your cost becomes higher. Let's try to revisit the initial graph problem again. So we don't have a problem with make set, it's very fast. Find set is very fast, but union is the length of the longer set, and on average, union is going to be big O of n, or not on average in the worst case. Because what can happen is you have a set of size 1 and another set of size 1, you make them union, you get a set of size 2. But you try to union it with a set of size 1, and the cost of this union is going to be 2. So first was 1 plus 2. And remember, if there are n elements, maximum times that you can run union is n minus 1, because after that you have all the elements in belonging to the same set. So first union will be cost 1 because one back pointer was changed. Here the cost of union these two will be 2 because two back pointers need to be changed. And you'll end up with a set of size 3. What happens when you try to union it with a set of another size 1? You have to change 3 back pointers and the cost is 3. So until it may happen that in the end you have n minus 1 elements in one set, one element in another set, and you try to make them union and the cost is n minus 1 because you have to change all these back pointers. Essentially doing this n times is order of n squared, which is not good. So worst case union is going to be big of n. You do it n times, it's order of n squared, not good. So overall your complexity for this becomes OV, but overall this union thing is giving us a problem. It's still making our solution OV cube. We already had a V cube solution. Why to learn a new data structure then? I'll tell you why. We can improve this. A very simple heuristic, if applied, reduces the time complexity. So whenever you're trying to union two sets, just take the smaller set and attach it to the larger one rather than taking the larger one and attaching it to the smaller one. So let's say union x comma y, x has more elements than y, then attach y to x. But if x has less elements than y, then attach x to y. So that's all. That is the weighted union heuristic. And does it really help us with the time complexity? I'll tell you how it helps. So when you do this, the cost previously we discussed why it was coming up n square was because of changing too many back pointers. Now let's think of some element x. X was initially a part of a set where it was the only element and it got attached to someone else. Okay. It became a part of a set that has to have at least 2 elements. Cool, good enough. And you change the back pointer of x one time. Now, once you do it again, let's say the back pointer of x changes once again. What happens now is the set to which x will belong needs to have at least 4 elements. Why is that? So because we are attaching the smaller set to the larger set, the other set needs to have at least 2 elements. Otherwise, we would not have changed the back pointer of x because the other set would have got attached to this one. But since x's back pointer is getting changed, then the other element set has to have at least 2 elements, and only then we would be attaching it to the other set, let's say AB. And your set size becomes 4. If you do it once again, that means x back pointer changes again, then your set needs to have at least 8 elements. Do it again, your set needs to have at least 16 elements. So for any element in your overall disjoint set union collection, if the back pointer is changed k times of a given element, that element needs to end up in a set of size 2 power k. And since this is true, k can be no more than log of n base 2. So you will not be able to change the back pointer of any single element more than log n times. And since there are n elements, overall running union n times will be n log n. So amortized complexity for union operation per union operation will be log n. And this is the good news. Let's revisit the problem again. So now make set is O1, find set is still O1, and union is amortized log n. The solution we had V cube is now V square log V. Amazing. The good news is that it can actually be improved further. And we have a forest implementation of disjoint set, which keeps these sets as tree-like structures as seen here. And every node has a parent pointer, except the and even the representative nodes have a parent pointer, but they point to self. So for this particular set S1, for finding the parent, for finding the set, for find of E, you will go to the parent of E, which is C. Then you'll go to the parent of C, which is A. And since the parent of A is itself, that means it's the representative, and find of E is actually A. Similarly, find of B is A. And All you have to do is keep traversing the parent pointers whenever you are asked to do a find operation. Now, we will discuss the complexity of find operation in some time, but let's discuss make set. So make set is very easy. Just create a new node, make its parent pointer point to itself, and you're good. O1. How about union? Union is also very easy. So all you need to do is, if you are asked to union D and H, find the parent pointer of find the parent of A or D, basically the find of D, which is A, find of H, which is G, and then union them. So A's parent pointer starts pointing to G. The problem here is find may be costly, but ignore find for now. We'll think how we can improve its complexity. But otherwise, union is nothing but changing one pointer to the other parent, and that's it. So if you want to union these two sets, change the pointer of F, parent pointer of F to G. So essentially it's very fast, except if you are asked to union B and H, and you'll have to first find out which is the set they belong to using find, and that may be costly. So let's see what find could be. So in a worst case scenario, you may actually end up having a tree like structure which is actually a linked list. So B, C, so until F. So if I were to do find of F, I'll have to go all the way up to A. This is going to take big O of n time. Find here is not good, but we can improve it, and I'll show you how. So union is O of 1 into whatever is find, and I'll tell you how to improve find. So O of 1 into whatever is the complexity for find, which we can improve. Make set is O of 1, very good. Find is currently O of n, but we will be improving it to much better complexity using two heuristic algorithms that we'll study. So here is one of the heuristic. Whenever you are doing a union, always do it either union by size or union by rank. So if you have two trees that you're merging together, take the smaller tree and the representative of the smaller tree should be attached to the representative of the bigger tree. This is one heuristic. Or you can take the two trees, whichever has lower height, attach it to the one that has higher height. And just by ensuring union by rank, what you're essentially ensuring is your length, overall height of the tree does not go above order of log n. So it will be sometimes log n, but not more than that. That already reduces your finds complexity to log n, which is amazing. But we can do better actually. Let's see how. The other heuristic that is the magic is path compression. Whenever you run a find operation, reduce the path. So if this was your set here before running a find of D, after running find of D, whatever is the representative you find, you make your pointers map to the actual representative rather than mapping it to B. This does not add any value, and since I'm already going up all the way up, might as well change some extra pointers. How it's implemented is going to be quite simple through basic recursion, but the idea here is that your path will be compressed every time you run find of any element, and at the end your set will start looking something like this, everything mapping down back to the single element. And what happens is when you map these together when you implement a structure with both these heuristics together, your complexity reduces down to something very small. What happens is your make set becomes O1, find set becomes, this has to be union. So union becomes O1, and find is amortized big O of alpha n. Alpha n here is the inverse of the Ackermann function ak1, and now this inverse alpha n, the value of alpha n is less than equal to 4 for any n up to 16 raised to the power 512. This number is much greater than 10 to the power 80, and just to understand how huge this number is, 10 power 80 is the number of atoms in the observable universe. So for any practical purpose, you can consider alpha n to be less than equal to 4, which is a constant, any practical purpose. And this means your union and find both become O1, your make set becomes O1, and this is super amazing. The proof I have omitted for this video because it's pretty hard for a small video. I would recommend go and read this book. There's a very brilliant proof of how this is there, but it's sort of hard. The point to note here is that this, for all practical purposes, is going to be O1, all three operations. Now let's revisit the problem again. Now, since everything is O1, your complexity reduces down to v square alpha v, which is v squared. So you were solving a problem in v cube, which you are now solving in v square. So that's the power of the disjoint set union data structures. If you want to learn more about the applications, you want me to write a good library for this, solve some problems using this, you'd like to see code snippets, make sure that you like the video, leave a comment that hey Karthik, we like the video very much. That makes me very happy. Subscribe to the channel and I'll definitely make more content related to this, maybe an entire playlist. For now, here are some applications. You can find cycles in a graph. The Kruskal's minimum spanning tree algorithm directly uses DSUs. For learning more about these, you can look at the references. So thanks for watching the video. I hope this helped and let me know in the comments. Bye bye.